In this video, we're going to be learning about the kinematic equations. So first, the kinematic equations describe motion while ignoring the agents that cause the motion. So here we are not talking about forces. Also, the kinematic equations can only be used when there is constant acceleration. So there are 4 kinematic equations, and I would prefer you to write them down in this order. So we're going to be referring to them by number. The first equation is VF equals VI plus AT. So this is final velocity equals initial velocity plus acceleration times time. Now you would use this equation for a problem like this. A bus slows down from 12 meters per second to rest with an acceleration of -3 meters per second squared. How long did it take the bus to slow down? So we're given from 12, so 12 would be our VI, our initial velocity. Rest, or 0, would be our final velocity. Acceleration would go in here, and then we're asked for how long did it take the bus to slow down. That refers to time. So then we could just solve for time. Here is our second kinematic equation. XF equals XI plus VIT plus 1/2 AT squared. So this stands for final position, so 10 meters, 50 meters, 100 kilometers, whatever. Initial position. Initial position will usually be the 0 mark. Then we've got initial speed, time, and then again acceleration and time squared. You would use this equation for this type of problem. An airplane accelerates from rest down a runway at 3.2 meters per second for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. Okay, so this problem does not give us final velocity, and this equation does not give us final velocity, so that's why we want to use this. Let's go into this in more detail. So from rest, initial velocity, down a runway at 3.28 meters per second squared, that's our acceleration, then 32.8 seconds, and then we want to determine the distance. In this case, distance would be the same as displacement. We would assume that our initial position is 0, so we would be looking for our final position, or the total distance the airplane travels down the runway. Here is our third kinematic equation. So final velocity squared equals initial velocity squared plus 2 times the acceleration times, and this is just the displacement, so final position minus initial position. You would use that equation for a problem like this. A driver of a car traveling at 15 meters per second applies the brakes, causing a uniform deceleration of -2 meters per second squared and slows to a stop. How far has the car moved during the braking period? So in this case, 15 is our initial velocity. -2 would go in for A. And then VF, that would be 0 because it slows to a stop. And then we would assume that XI, or initial position, is 0. So again, in this one, we'd be looking for XF. Now you may ask, why couldn't we just use kinematic equation number 2? Well, the answer to that is this equation does not involve final velocity, which we're given. This equation, equation number 3, does not involve time, and we are not given time. So this is the perfect equation to use. And then equation number 4, which we probably won't be using as much, is final position equals initial position plus 1/2 times VI plus VF times T. And you would use that equation for a problem like this. A bike accelerates uniformly from rest over a distance of 35.4 meters in 10 seconds. What is the bike's final speed? Okay, so we're given the distance, which would refer to final position, because again, we assume that initial position is 0. We're not given the acceleration, which is fine because this equation does not involve acceleration. We're given the time, which is 10 seconds. Our initial speed is 0, that would go in here. And we're looking for VF, or the bike's final speed. So in the future, we will be using these equations quite often.